Alright, so I'm going to do a drawing on here showing the true shape of Earth using WGS 84 coordinates. So it's in three-dimensional. So you get the geoid, which is gravity using the ocean. So you subtract the geoid height from your elevation to get the ellipsoid. So that's kind of basically how that works. Like for state plane coordinates, for every state, they have zones. Like here in Kansas, we got two zones, north and south. And so you can see grid for the projection is shorter than the ground distance. So you have a combined scale factor. And you can see the ellipsoid's curved instead of straight. So it's kind of like the best fit, I guess, best fit around the globe, you know. So that's what I'm doing here. So let's see. So in my drawing, how do I come up with those points? So I'll go ahead and erase this line. I chose 90 degrees. So is what I'm doing. Open up Google Earth. And so I chose 90 degrees at the equator because it kind of cuts through United States. So I'm going from here all the way to the North Pole. So so here's, well, that's not it. Let's see here. WGS. So here's my points. I did it 0 degrees, 10, 20, 30, 40, and then 60 and 90. So I use XYZ Zen when so I get my latitude and longitude, which is 0, 0, 0.00, and then I'll go 90.00 decimal. And I got to go to this website because in the ocean I'm out of range because it's, you know, 0, I guess, for the elevation for that, but there's a geoid there, and subtract the ortho height from the geoid to get the ellipsoid. So so on here we'll go 0, 0, comma 90 or minus 90, comma, we'll just say 1. It's in meters because there's, you know, maybe some high tide or something. So we can see that the dot is right there and it's a -4. So in XYZ, I'm going to put -4. I could have put -3 really, but so -4.00. I'll say I convert. And you should see, so that matches that for my 0. Let me see what I did for Not sure what I did used for 10 degrees. Let's see here, 10 and submit. So I probably used 1, maybe. I'm not sure. Let's see. Negative. 10. Convert. Oops. 0.00. Convert. So I got lucky. Yep, looks like the same. 3, 4, and then that's number matches that number. And so I basically said 1 and then subtract 2. So I don't know, I just chose 1. So that's why I have 1 there. So we go into 20. So minus 11. So I probably did minus 11 on that. Let's see here. So XYZ. So 20. So minus 11. Convert. Let's see what I used. Damn it. Come on, I got so much stuff open. Let's see. So I did that matches at 20 degrees. I went minus 11. So 0255 and 0255. So I kept doing that all the way to the North Pole. Get rid of all this, and this. Okay, so we're getting AutoCAD. So I'm going to delete those points and re-port them back in. Delete. They're gone. Okay, I'm going to import. PNAZD. Next, and so the points are back in. And then I just draw a polyline, which is this here. Let me change my view. UCS XY. And XY. Okay, so beeline. So I'm going to connect the dots is what I'm going to do here. Arc. Second point. Yeah, it's not. I'm in the wrong. We'll just do it like this. Okay. Same thing. So beeline. Start here. Arc. Second point. And just draw drawing it along here. And to the North Pole here. Alright, so we'll go back to that view, and so that should be the same distance. So let's see here, length 30, was it read the last 4 digits, 3820, and hold on, length 3820, length, okay, so I messed up. P-line, arc, second point, probably missed one. Alright, here we go, rocking. In there though. So we'll go right there. And it now 445 copy. Alright, so 4450 for the length. And this is 4450, so they're the same. And even set it on top there. Same thing. Alright, now, is what I want to show is the distances. Oops. What? So for the radius, and then I'll get into that, and I'll get the drop and some other things. So bear with me here. Alright, so for the radius, so I can get rid of this. Alright, so I got 3963. So if you read here, the sphere will it so 3963. So the Earth is approximate an oblique spheroid known as the reference ellipsoid. Instead of a sphere, which it's not, we use the spheroid whose radius is this number right here. So 3963.19. And I got 3963.19 at the equator. Okay, at the equator. Now we got to do for the poles. So it's 3949.90. And I got 3949.91. That's close for me. So let's figure out I guess the circumference. So we got that arc length. A bunch, there's tangents, but it still gets okay. Everything's in meters in this drawing, so copy. So this, paste, and so I got 6214. So if I take 6214.885 times 4, because that's one quadrant, and then I get 24,859. Okay, so circumference. So Earth's circumference is the distance around the Earth, measured around the equator. And we'll get to that one. Measure, I just did the one around the poles. So measured around the poles, the circumference is 24,859.73 miles. So I got, 859, and I got, wait, hold on. Where's my calculator? 24,859. And so 24,859.7, I got .5. Close enough. Okay, so now we need to know the measure distance for the equator. CAD. So I just take this, copy. And I'll just copy this. And I'll just draw a circle for that. And circumference is it's in meters. Paste. So 24,901. So this thing got 24,901.4. And I got .5. That's real close. Alright, so alright, let's measure this drop right here. I need to take arc. Oops, arc. So we got 50. Kind of doing it in reverse, but it should be. Let's go plan. And then switch it. Should be the back. I don't know. But it's 50. Alright, so I'm just doing my view kind of different than I'm normally used to. Okay, I think we're done with this. Check that out. So get my calculator. So we use 39, 59 minus 39, 59, which number I don't like, times cosine. I think what, 50? 50. So 50 degrees. Enter. So I got 1414. And I get, for the drop there, so I got 1415. So 1415, and 14, 15. It's like barely off. 1 mile. 14, 15, 50 degrees, 39, 59. So it looks right. So we'll just measure do the, figure the calculation of the 50 degrees. So I did 50 divided by 360. Times 2 pi. And then 39, 59, 39, 59. It should give me the arc length. Equals. Let's see if I get that. So from here to here, trim. I'm gonna do it this way. Break. And then distance. $34.54. $34.54. Yeah. That's why I don't like that number. If you use, because okay, we'll do this angle. This is what I meant to do. Let's see here. Okay, so back to my calculator. Clear. So we'll take sine, clear. Oh, my distance. So 30, 40. So 30, 40. And then divide that by 39, 59. So it's 50 degrees. I was a little off. That's why I don't like that 39, 59. It's a generic number. Don't like it. Alright, so I'm gonna do, so we'll do like 1 degree. So copy. Rotate. undo. Something like backwards. Rotate -1 degree. So it should come up for that, for the 1 degree. 1 degree of latitude. Alright. Trim. So for this, I get $69.17. So that checks out. Excuse me. So let's do a different one. I'll do. Alright, so let's check out like maybe between these two. So 10 degrees. Alright. So we did this. Check that. So clear. So 10 divided by 360 times 2 pi. I do not like this number. 39.59. Boom. Enter. 690. So, let's see what I get. So, length should be fairly close. My stuff's accurate. Keep you right getting rid of that. So 688. And that thing said what? 690. So 88. Yeah, 88. 688. Maybe not a couple miles off. It's because I'm using 30. That's not really the radius of the Earth. It's just the mean radius. You know, this here. So that's why they use that. Because I get this number and the equatorial, and then for the equator, I get this number, 3963. So 3963. So these two are not even. So it's just not going to work. Alright, so I got that. Alright, now I did the circumference, the radius, the drop, the angles. Now let's build it and see what it looks like in 3D. So basically this is this. Let's see here. View. I need that. So revolve. So that's really the true shape of Earth right there. What the hell? Put a little hole in front of there. Oh, I know why. Let's see here. But you can never tell. Alright, so let's see what that is. Angle 70. 79, 26. So yeah. But let's draw a circle of the radius. So miles to millimeters or meters. So 39, 59. Radius. Can't really tell. It's almost perfect. But it did fit it pretty good. So with this, by using those coordinates that I did with the geoid and placing those points in there, the cocoa points, gives me the shape of the Earth. So let's see what I get again for this. Linked. I'm gonna use Google Earth. Copy. Oops. We know that. We know all that. So I need meters to miles. Paste. So what I'm looking for is 6214. So I believe this is using WGS 84. So this is what I did right here at 90 degrees. So we'll measure it Close enough. I got 6214. 6212. 6214. As you can see, the ground 6214. So I just pretty much proved all that. So I did the drop, this. So it's elliptical.